Okay, VSEPR Theory. So we've done the model building activity in class. So this video is meant to be a summary of what you discovered in class with those models and a few tips, and a review for you. So we know the theory, the letters stand for valence shell electron pair repulsion. The key is to look at the valence shell electron pairs of the central atom. So focus in on the central atom. Remember that the electron domains are positioned to minimize repulsive forces, and that lone pairs repel bonded pairs more strongly than bonded will repel bonded. So the first example here is BeCl2, and you can see I've drawn the Lewis diagram. So the focus for us then is to key in on the valence shell electron pairs around the beryllium. And we can see there that there are two electron domains. Both of them are bonded. So we're looking to position these electrons so that they minimize repulsion between them. And really that sets up then as the linear arrangement. So it's important that those bonds look 180 degrees from one another. And so we label the bond angle here as 180 degrees. This shape is known as linear. And if you were to build this model, if you recall that, you can see then that all the atoms are in the same line, hence the name linear. Okay, moving to the second example, BH3. Now when we draw the Lewis diagram of BH3, recalling that boron is one of the exceptions, we see that there are 3 electron domains, and they are all bonded. So now the question becomes, to apply the theory, how do 3 electron domains arrange themselves to minimize repulsive forces? And as you saw in class today, these bonds look to arrange themselves 120 degrees from each other, essentially divide a circle by 3. And we finish then with this trigonal planar arrangement. So up in this linear arrangement, I didn't write in the general formula there. We had A as a central atom and B as a bonded atom. So in fact, it was AB2. In this trigonal planar arrangement, we see AB3. Okay, moving on to the SO2 molecule. So if you haven't already drawn a Lewis diagram for this, I would pause the video and do so. Okay, so I've positioned the atoms on the page. There are 18 electrons to place in the diagram. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Checking stability around the sulfur, it only has 6 electrons, so I need to reposition and make a double bond. And so I finish with this structure. Focusing in as we do on the valence shell electron pairs of the central atom, I notice then that there are 3 bonding domains. So one is the single bond. This is one domain. The lone pair is a second domain. And this double bond counts as one domain. So there are 3 electron domains. So we think just like the previous example, the 3 electron domains will arrange themselves 120 degrees apart. Well, almost. We have a lone pair in place of a bonded pair. And so I do need to show these bonds to the oxygens going off at an angle, but in fact we can expect that because lone pairs repel bonded pairs more strongly than bonded pairs do, we can expect a greater repulsion here that will essentially force this bond angle to be less than 120 degrees. And in fact, we do observe that in molecules. So the general form of this, the sulfur is the central atom, that's A. Then we have 2 oxygens, and there's 1 lone pair, so AB2E. This shape is referred to as bent. It's also referred to as V-shaped, so you may see that in some reference. Okay, moving on to CH4. So we've covered off 2 electron domains and 3 electron domains. Now we're moving into 4 electron domains. So pause the video, work a bit ahead of me, and draw your Lewis diagrams for CH4. Okay, so we can see the molecule of methane, 4 single bonds between the carbon and each of the hydrogens. Counting the electron domains, again focusing in on the valence shell electron pairs around the carbon, we see 4 electron domains, all of them being bonded domains. Now, you may be thinking, well, they do look equally spaced apart. Like this is 90 degrees, this is 90, this is 90, and this is 90. But what about the angle between this bond here and this bond here? Isn't that 180 degrees? So why would those 2 bonds be so much further apart from each other if all these bonded electrons are repelling each other equally? And the answer is, in fact, they're not. It takes on a 3-dimensional shape, which you would have seen when you built the molecule. So when we draw this shape with 4 electron domains, all of them being bonded, we set up, first of all, the 3 atoms that are in the same plane. So 2 of the hydrogens and the central carbon. And this bond angle here should not look 90 degrees. Make sure when you draw it, it looks a little bit larger than that. So the bond angle is 109. And then, as you saw with the model, we need 1 bond to a hydrogen coming out of the page, and then a second one receding into the page. Now, you can either show the receding one like I just did there, or as I redraw it here, with 2 lines, the wedge, you could do just a dotted or dashed line to the back. So either of those are acceptable. If this shape doesn't mean something to you as you're drawing it and you haven't built the models yet, then it would be well worth your while to build this and compare it to the diagram. The name of this shape is tetrahedral. Okay, so our next example here is NH3. So as you draw a Lewis diagram for NH3, you'll notice the 8 electrons distribute into 4 electron domains. This time, oh, I just realized I forgot to write the general formula for CH4. So there was AB4. This time we have 1 central atom, 3 bonded atoms, and a lone pair. So looking back then at the CH4 molecule, essentially what we're doing is replacing this top hydrogen and these shared electrons here with a lone pair. So I'm going to keep this line, keep the wedge, and keep the receding, and just put a lone pair here instead. So when I draw it, I have the nitrogen with the lone pair, the atom in the same plane, the atom coming out of the page, and the atom receding. Now, do you think this bond angle is still 109, or has replacing the bonded pair with a lone pair changed the angle? Hopefully you're remembering then that lone pairs repel bonded pairs more strongly, and so in fact there's a greater repulsion happening here, and that leads to this bond angle being 107. When you built this molecule, you would have noticed the pyramid type shape that you formed, and it is called trigonal pyramidal, not to be confused with trigonal planar. Trigonal planar did not have this lone pair here, and that makes all the difference. Okay, water is another example of a molecule that has 4 electron domains, but it does follow a different order than what we've seen so far. So there are still 4 electron domains, but now we notice there's 1 central atom, 2 bonded, and 2 lone pairs. So now we have 2 lone pairs. The way to think about this is essentially it's much like this methane molecule, except now I'm going to leave these 2 bonds here and replace the receding and the wedge with 2 lone pairs. And so in fact we end up drawing this in 2 dimensions. Just move back up to the water. So we end up drawing this in 2 dimensions. I could draw it like this with the lone pairs here, or I could have drawn it like this. Again, you're very familiar with the shape of a water molecule, but hopefully you're understanding that shape a little bit better now. Are these 2 lone pairs repelling those bonded pairs even more strongly than the 1 bonded pair on the nitrogen repelled those? Absolutely. And so we do see a bond angle here of 104.5 degrees. This shape is referred to as bent, which again could also be V-shape. So most of the shapes that we look at do fall into the ones that I've explained so far. And maybe, 15% of the others that expand beyond, where the central atom expands beyond the octet, will fall into the category of 5 or maybe even 6 electron domains. So I'm going to address these in terms of the different types of shapes and work from their general formula. You can look back in the table activity on page 209 and 210 to see specific examples, and you can do the homework, and that will help you with more examples also. So when you drew the Lewis diagram for a central atom that was bonded to 5 bonded atoms, you likely just positioned them like 5 spokes of a wheel. And when you build this molecule, you'll actually observe the central atom to have, and if you view it like the Earth, to have a bond coming out of the North Pole, so to speak, and the South Pole, and we refer to those as the axial positions. So there are essentially 2 axial positions. Now, running around the center of the Earth is the equator, and that's essentially where the remaining 3 bonded atoms appear. So this is much like a trigonal planar structure from the side, at least these equatorial positions. And so that's what these are, the equatorial positions. So you'll see bond angles here of 120 degrees, a bond angle here of 90 degrees, and going from here all the way to here, that's 180 degrees. So this shape is referred to as trigonal bipyramidal. And hopefully you can see the idea that there are 2 pyramids, so bipyramidal, right? The idea that we have a central atom here, right? And 2 axial positions, and then 3 equatorial positions that essentially build up a pyramid on top there, and then a pyramid on the bottom. So it's a little bit tricky to see there. It's a little bit tough with the dimensions. Okay, so there are 3 equatorial positions and 2 axial positions when there are 5 electron domains. So there are a few shapes that come off of this one. Let's say that central atom is now, instead of having AB5, we have AB4, and there's 1 lone pair. The key with these 5 electron domain is to replace an equatorial position. That's the key. So replace a bond that's in the equatorial position with a lone pair. So that's where the E goes, if you will. So if we have A in the middle, we still have our 2 axial positions, but now the bond that was previously moving out here to the right is now going to have a lone pair. And I still have the wedge and the receding. And if you were to turn this on its side, it would kind of look like this, which essentially sets up like a teeter-totter. If you were to push this back and forth, it would rock. It's a little bit hard to see the dimensions there, but it sets up the shape seesaw. So we still see the 120 here and the 180 between the axial positions. Now, to continue with 5 electron domains, I'm trying to squeeze this in so you can still see the original structure with AB5. So now what if we were down to 3 bonded atoms and 2 lone pairs? So continuing to replace equatorial positions, I'm going to put the 3 bonded, so 2 in the axial, 1 in the equatorial that's in the same plane, and then it's the wedge and the receding that I will replace with the lone pairs. So this bond angle is 90 degrees here, and this bond angle from here to here is 180 degrees. This sets up, if you can view it, maybe I'll do it in green, or that might get a little bit messy, but here, I'll twist this on its side so you can see the bonds that are in the same plane. And can you see how this essentially forms a T? So this is called T-shape. Okay, and last bit then, the last option for 5 electron domains is to replace 3 of the bonded pairs with 3 lone pairs. And so you'll see then that all equatorial positions are replaced, and we finish with lone pairs in the 3 equatorial positions. The bond angle here is 180 degrees, and you'll notice that the atoms all line up, and so this is the linear shape. Okay, very last part of the lesson then is to look at the 6 electron domains. So if we had AB6. So this is the idea of having 6 electron domains. So with 6 electron domains, we still think of the central atom like the Earth and have axial positions. And then in the equatorial, there's actually 4 equatorial positions. So they set up kind of as a square in running around the equator of the Earth, if you will. So in terms of bond angles, these here are actually 90 degrees, and we still see the 180 between the axial positions. From an axial to an equatorial position would also be 90 degrees. Okay, so the shape then of this, or the name of this shape, is called octahedral. All right, now the trick with the 6 electron domains that's going to be different than the 5 electron domains is that if you're going to replace bonded pairs with lone pairs, now you replace the axial positions. So there will only be 2 more shapes then that we derive from these. So for example, if we had 1 central atom, 5 bonded atoms, and 1 lone pair, we would have our central atom, and instead of having 2 axial positions, we would just have 1. So I chose the top one, the north point of the axis, if you will. And then we show the same equatorial, 4 equatorial positions coming out here. And if you didn't label that, then it might be worth labeling that here to recognize the 4 equatorial and the fact that there are 2 axial, your north and south. Okay, so now we've removed one of those axial positions, and we can see that we still have the 90 degrees here, and we still have the 90 degrees here. So this shape is then a square-based pyramid, which we can then call square pyramidal. So definitely setting up a square here, right? Based pyramid. There we go. Okay, and last option then is to replace the 2 of those original 6 bonded with lone pairs. And so we replace both axial. So both axial positions have the lone pairs, which just leaves those 4 equatorial positions. So a side view then shows this square planar structure. We have 90 degrees here, and call this square planar. Think about it, if you remove the axial positions, that this square would essentially just sit flat right on the table, square planar. Okay, that's it. So bring your questions in and lots of practice, and it will get better the more you practice.